Okay, this video is to go over a special case of rotational motion called rolling without slipping. So let's look at the possible cases of what rolling without slipping is going to look like. So if we look at the first situation, let's just say that this object here is just sliding. Okay, so think of it as like here's my tire right here, and I'm riding along, rotating along, oops, and I hit the brakes and then I just slide. Okay, so that's what we're looking at, just sliding motion. So if we look at the velocity of the axle, which is where it would rotate about, that's going to be the same velocity at the top and at the bottom because it's just sliding along. So it's going to have some velocity v, which will be the same at the center as well as all the strings. Again, remember, it's just kind of just sliding along, skidding. Okay, so let's look at what we're going to combine that with, and that is just an object that's just rotating. So let's just look at our object that is just rotating in place. So about the axle, well, that obviously doesn't have any speed associated with it, but if I look at these points at the tangents here, and let's say my object is rotating this way with some angular velocity, it's going to have a tangential velocity, we'll call it v sub t at the top, and then of course if it's spinning around here, at the bottom it's going to have an equal tangential velocity going the other way. So when we're looking at this special case of rolling without sliding, we're looking at this object that is not only translating, the center of mass is moving along, but it's also rotating. So let's look exactly what's going on with just a particle at that point. So I'm going to line up the arrow on my tape here with this little point right here, and then we're going to see how far it rotates, and this may be very obvious to many people. So if I'm rolling without sliding, it's moving along until it's done one rotation right there. So it's gone this distance from here to here, and I don't think it's too much of a stretch of imagination to realize that that distance is going to be equal to the circumference of the circle, which is 2 pi r. So if I look at my object once again, the center of mass has moved that same distance. It's moved a distance equal to the circumference. So the tangential speed is going to be equal to the speed of the center of mass, which is going to be equal to 2 pi r over the time it takes it to go that distance, and we can recognize this as just r times omega. So once again we see this condition for rolling without slipping, again our non-slip condition, that our tangential speed is going to be equal to the speed of the center of the mass, which is equal to the radius of the object times its angular speed. So we're going to use that information to put together what rolling without slipping is going to look like. So we are taking something that is sliding and we're going to add to it something that is just rotating to get rolling without slipping. So if we look at our velocity vectors, we're just going to add them. If I look at the center of mass, well, it's got a velocity here when it's sliding. If it's rotating, that center of mass is not moving at all. So we are going to get a speed of that center of mass right there, and if it's rolling without slipping, that center of mass is going to be equal to the tangential speed r times omega t. Okay. We look at what's happening at the top here. Well, sliding, it has the speed of v. This is going to have a speed of vt. So if this is just the same velocity, that let's assume, like we had from this case right here, that our tangential velocity is going to be the same speed that its center of mass is moving. That's the condition of no slipping. Then this is just going to be equal to, this one. Then these two are going to be equal to each other. So that's the condition of rolling without slipping. So at the top, it actually has a speed equal to twice the tangential speed, or twice the speed of the center of mass of the object at the center. Then if we look at what's going on at the bottom down here, these two speeds are equal in magnitude, pointing in opposite direction. At the very bottom of the rotation, it's not moving at all. So instantaneously, it's not moving. So this may be hard to kind of visualize or actually convince yourself that that's true, but again, if we look at, and I'll put my ruler in here so I can do this, as this object rotates, and if I could rotate it at a constant speed, momentarily when it hits the bottom of the rotation, it's actually going to be not moving at all. So this is kind of the foundational piece of what rolling without slipping looks like. So now what we want to do is actually analyze the energy associated with an objects that are not only translating but rotating as well. So we need another piece of paper for that. And we'll slide one in here. So there we go. And let's look at an object. Let's just look at what our kinetic energy is going to look like. So we're going to have something that is rolling and sliding. So rolling without slipping. It's going to have kinetic energy associated with the translational motion, which we are very familiar with, is 1/2 m velocity to the center of mass squared. Plus, it's going to have kinetic energy associated with the rotation, which, and we're ready for it, wait for it, here it comes, it's going to have a rotational analog. Rotational analog of mass is its inertia. Rotational analog of its velocity is going to be its angular velocity. So the kinetic energy associated with rotation, 1/2 I times omega squared. So our total kinetic energy for an object that is rolling without slipping is going to be equal to the kinetic energy of translation plus the kinetic energy of rotation, which we know is going to be equal to 1/2 m v center of mass squared plus 1/2 rotational inertia times omega squared. So we're going to do a little algebra fun here and simplify some things so that we can get a more conceptual idea of what's going on here. So what I want to do is I want to factor out our commonly used translational kinetic energy. So I'm going to factor that out of the problem here. 1/2 v center mass squared. So factor that out. That's just going to be a 1 there. And here I took a mass out here, so I got to put a mass on the bottom over here. So we're going to get a rotational inertia is going to stay in there. I'm going to have a mass here. And instead of omega, I'm going to put in our non-slip condition where omega is going to be equal to v over r. So we're going to put that in there, and the v squared has already been factored out, so I get an mr squared right there. So I squared that, and omega squared is v squared over r, and then I factored out the v squared right there. So this is kind of interesting to take a look at, our total kinetic energy. It's equal to, this 1 here is going to represent the translational kinetic energy, and then this factor right there is going to represent our rotational kinetic energy. So what does this tell you? If I remember some of our formulas for moment of inertia for different things, if we look at a point particle, or if we look at a ring or a hoop, if we look those up, they actually have a moment of inertia equal to 1/2 mr squared. And these are actually the biggest values of the moment of inertia we have. Everything else is going to be less than that. So aside from just a point particle or a ring or hoop, sometimes they're called a hoop, has this moment of inertia, everything else is less. For example, if we look at a disk is 1/2 mr squared. If we remember the rod, if I swing it, it either is 1/3 ml squared, or depending where the axis of rotation, it can be as small as 1/12 ml squared. So these are going to be much smaller. So we can see this condition that our moment of inertia is going to be mostly less than or equal to mr squared. So if we see that our moment of inertia is mr squared, the biggest it's going to be, in the case of a point, a ring, or a hoop, is 1 plus 1, or 2. So we're going to see that half the total energy of our system is going to be due to translational kinetic energy, and half will be due to rotational. That's the maximum it can be. For most all these other guys, the disk, the rod, spheres, they're all going to be much less than that. So a rotational kinetic energy is at best going to be equal to the translational kinetic energy, but for most everything else it will be less than the translational kinetic energy. So that's kind of an important conclusion that you can just see it looking at some of the algebra. Now let's look at conservation of energy. Yeah, we got to do that. Another piece of paper. Here we go. So let's put, and this is a common AP problem, a sphere, lacrosse ball, something like that, bowling ball at the top here. We're going to make it a solid sphere. It actually has a moment of inertia equal to 2/5 mr squared. So if you remember, I told you that mr squared was the biggest. This is the moment of inertia of a sphere. So let's say this has mass m and it has a radius r, and we are going to put it at a height equal to big H. So let's say I want to find what is the velocity of the center of mass at the bottom. Well, we found we can do kinematics with this, but that actually is a bit of a nightmare, and I think a little bit more than what we need to do in this class. Or we can use energy, and it's a little bit more simple. So our conservation of energy is going to say that our total gravitational energy at the top has to equal our rotational kinetic energy plus our translational kinetic energy. So I'm just going to kind of put these through, and we're going to see what it looks like. So at the top, we're going to get M is our mass of the ball times G times big H. And I'm going to use that total kinetic energy that we talked about before, that we derived on the last page. 1/2 m center mass squared, 1 plus rotational inertia over mr squared. Okay. Again, this is our translational factor, and this would be our rotational kinetic energy. So now if I solve for my center of mass, we get velocity to center mass. Cross multiply, I'm going to have a big square root, and on the top here, look at this, our masses cancel out. We saw that before, masses cancel out. I'm going to get a 2gh on the top. Well, that already looks a bit familiar. We've seen something that looks just like that before. And then if we divide through on that, we're going to get 1 plus the rotational inertia over mr squared. Okay, so this is how we can solve for the velocity at the bottom. So conceptually, what can we see? The bigger the rotational inertia is of our object, the more energy gets transferred into rotational kinetic energy. So if I have more rotational inertia, it's going to have more rotational kinetic energy. That means it's going to be going slower. The center of mass, the velocity of it, is going to be less than, it will be decreasing. The bigger the inertia, the smaller the speed of the center of mass at the bottom. And you can kind of see that from this, the way this expression is written out. So best case, if this was a hoop where my rotational inertia was 1/2 mr squared, the best case, half that kinetic energy would be rotational and half that kinetic energy would be translational kinetic energy. But here, so that's for like a hoop or a disc, but now we got kind of a small one, a sphere, 2/5. Less of that energy is going to get transferred into rotational kinetic energy. So we can kind of see from just looking at these equations how it develops with doing rolling without slipping. Okay, that's it.